It takes a force to move anything. The force to rock this sailboat obviously comes from the waves. If the waves can exert a force on the sailboat, then they must have energy. Where did they get their energy? The energy of the motorboat's engine pushes it through the water. Some of this energy is transferred to the water and makes waves. The waves carry this energy with them and use it to rock the sailboat. So it takes energy to make waves. Once waves are created, they travel and carry the energy with them. Where does the energy to make waves like these come from? On a day when the wind is not blowing, the water surface is often smooth. But on a windy day, there are always waves. If wind can supply enough energy to push sailboats and make small waves, let's find out if wind can also make waves like these, or even these. This is a wave tank. It was designed for studying waves under controlled conditions. Air can be pulled across the water in the tank by a powerful fan at this end. The tank has glass sides so that waves can be seen from the outside. Watch what happens when we turn on the fan. At first, the wind makes only small ripples on the water. As the wind continues, the waves grow larger. The longer the wind blows, the larger the waves become. The waves are bigger at the downwind end of the tank than they are at the end where the wind first strikes the water. Now let's speed up the fan. The waves have grown larger. It seems that the faster the wind blows, the higher the waves become. They grow bigger yet as the wind blows down the whole length of the tank. The greater the length of water surface the wind blows over, the larger the waves it makes. The wind blowing over this lake strikes the near side of the lake first and makes only small ripples. But on the far side, the same wind has produced much larger waves. All waves travel out of the area where they were created. They continue traveling until they meet an obstacle, in this case, the shore of the lake. So when we see waves at the beach where there is no wind blowing, it usually means that the waves have traveled from somewhere out at sea where the wind was blowing, making waves. Waves like these are found where the wind has been blowing at high speeds in the same direction for a long time and over a large distance. The waves spread out from the storm area where they were created. They may travel thousands of miles before they lose their energy, usually at the shore. All waves on water are constantly traveling. But what about the water itself? Does it travel along with the waves? The ball stays pretty much in place, even though the waves keep moving forward. Why? If the same ball is dropped into a river, you know what will happen. Evidently, an object floating on water will move as the water itself is moving. Could this mean that the water in a wave stays pretty much in place and only the wave shape moves forward? Let's find out how the water in a wave does move. We'll use a wave tank again, but instead of using wind to make waves, we'll use a mechanical wave generator. The regular movement of the wave generator makes waves that are very much alike. These relatively simple waves are easier to study than the complex waves we find in the ocean. A small ball floating near the surface of the water behaves in much the same way as the larger ball did in the ocean. Let's watch it in slow motion. Each time the high point of a wave, called the crest, approaches the ball rises and moves forward with the wave. As the crest passes and the low point in a wave, called the trough, approaches the ball moves down and backward. After each cycle, the ball is back to just about where it started. The motion of the ball is almost circular. This means that the water on which the ball is floating is moving in a similar orbit. We can imagine that the ball represents a particle of water near the surface. By putting weighted balls into the water, we can see what happens under the surface. The uppermost ball moves in an almost circular orbit. But the deeper we go, the smaller the orbits become, and the slower the water particles move. Finally, at a certain depth, there is no orbit at all. If we measure the depth at which a wave no longer moves the water particles, we find that this depth is equal to about 1/2 the distance between two successive wave crests. This distance is called a wavelength. The deepest ball is at a depth greater than 1/2 a wavelength. The upper balls are less than 1/2 a wavelength deep. Now we know something about how water moves in a wave. But why do waves break as they approach the beach? This is a typical sandy beach at high tide. At low tide, we see that the beach is actually a gradual slope. As the waves travel into the shallower water on the slope, they break. Looking at such a beach from the air, we see that the closer the waves are to the beach, the shorter their wavelengths become. Notice the change of wavelengths from here to here. This must mean that the waves are slowing down and bunching up as they approach the shore. What is happening to the water particles within the waves? We have seen that most of the orbital motion in a wave takes place within 1/2 a wavelength of the surface. Here, the bottom of the tank is beginning to slope upward, like a beach. At this point, the bottom is a little less than 1/2 a wavelength under the water surface, and it is beginning to interfere with the orbital motion of the water particles. The circular orbits of the deeper water particles are being flattened. The waves are said to feel bottom. When this happens, the waves slow down. Nearer the surface, the water particles are orbiting faster, and the ones at the surface are orbiting fastest of all. As the waves move into still shallower water and slow down even more, a point is reached where the water particles at the crests are moving faster within their orbits than the wave shapes are moving forward. The result is that the crests of the waves pitch forward and break. The same thing happens on a beach. These waves moving into shallow water behave in the same way as the waves in the tank. As they approach shore, the bottom begins to interfere with the orbital motion of the water particles, slowing the waves down. Finally, the tops curl forward, the waves break, and give up their energy on the beach. As waves approach the coast, they may be traveling at almost any angle to the shoreline. But as they get closer, they bend until they are almost parallel to the shoreline. Why do they do this? We saw earlier that waves are slowed down more and more as they move into shallower water. This means that when waves meet a shoreline at an angle, the part of the wave nearest the shore is slowed down first. In the meantime, the part of the wave that is still in deeper water continues to move forward at normal speed. It will not be slowed down until it, too, reaches shallow water. The result of one part of a wave moving faster than another part is to make the wave bend. The waves moving into this bay feel bottom first just in front of the headlands and are slowed down, but they continue to move almost at full speed through the water in the bay. The result is that the waves bend toward the headlands and spread out in the bay. That's why the same waves that break hard against a headland break much more gently in a bay. The natural waves we have studied so far have resulted from wind energy being applied to the surface of the water. The container may be as small as a pond or as large as an ocean. This is the lighthouse at Scotch Cap, Alaska, as it appeared before April 1st, 1946. Early on that morning, huge waves destroyed the lighthouse and a radio tower that stood over 100 feet above sea level. About 3 hours after the waves destroyed the lighthouse, similar waves caused this damage to the Hawaiian Islands over 2,000 miles from Alaska. On the coast of California, a tide measuring station in Crescent City was recording the normal rise and fall of the tides. At almost exactly the same time that the waves hit Hawaii, this station recorded sudden large changes in the height of the normal water level. In addition to these 3 locations, unusual waves were also recorded at several other tide measuring stations along the coast of North and South America. The farther away from Alaska each station was, the later the waves arrived at that station. From the speed and direction of the waves, scientists calculated that the waves had spread from a small area of the Pacific Ocean off the coast of Alaska. The waves crossed the 2,200 miles of open ocean between Alaska and Hawaii in about 4.5 hours. By dividing the number of miles the waves traveled by the time it took them to cross that distance, we find that the waves must have traveled at an average speed of about 488 miles per hour. Waves traveling at these high speeds couldn't have been caused by wind, because wave-generating winds never blow that fast. What other ways are there of making waves? One other way is to apply the energy to the container itself. The waves that damaged Hawaii were created at the same time and place that a strong earthquake disturbed the floor of the Pacific Ocean. On the open ocean, the waves were only a foot or two high, and their crests were over 100 miles apart, so passing ships didn't notice them. Close to the Hawaiian shore, ordinary waves were lifted to extreme heights and washed over dock and waterfront areas. In river mouths, the waves appeared as rapid changes in sea level, causing seawater to rush far upstream. In some places, the waves rose almost 40 feet above the normal water level and caused damage more than 1/4 mile inland. Fortunately, most waves do not carry enough energy to do much damage. But all waves do carry some energy, and most of it is released against the shore. What effect do you think the energy of waves will have on this sandy beach, or on this rocky coast? Will this shoreline always look like this?